Okay, is it, when it comes to the final, is everything clear? Any more questions? Any more questions? So yeah. Okay, so let's reprove the third Sylow theorem. I'll reprove it. I'll redo the proof. And then I'll do some recap from the previous homework. So from homework to the bonus homework. Let G be a group. And H a subgroup of G. Let S be the set XH X inverse as X belongs to G. These are the sets of conjugates of H, right? Yeah? Set of conjugates. But again, if I said that the final is easier, don't like relax and then go there without having any clue. Keep working hard. Again, the goal, if you did not attend the lectures, if you did not see your notes, you will not perform well. Okay? So it's made, if you studied everything, you will perform well. If you did not study anything, you won't perform well. Okay? So coming like that, just like the midterm, if you studied everything and didn't have a bad day, it went well for almost everyone. So yeah. So this is S is the set of conjugates of H. Now from the homework, prop. Let's finish the prop. Then the cardinality of S is the index of the normalizer. This is finite. Or if G is finite, let's say. If G is finite, the cardinality of S is equal to the index of the normalizer, where NGH, what is NGH? It's the set of G's in G such that what? Anyone can help?
GH, G inverse plus H.
Very good. GH, G inverse is equal to H. Right? Now showing this as a subgroup is not very difficult. You remember in the homework, you've shown that this is a subgroup, right? In the extra bonus homework. Now you could show it by directly, but you can, if you express it as a stabilizer of something with regard to some action, then you get that it's a stabilizer for free. Do you remember this or not? Let's do this again. Proof. Proof. G acts transitively on S by the following. So you take G star XH X inverse. What does it give me back? Everybody, what does it give me back?
GXH X inverse G inverse.
Very good, Victor. Thank you. You remember this? Everybody, we've seen this? In the homework, G is in G and X is in G. The proof that star defines an action on S has been done in the homework. Now what can I say about this action? It is transitive. Why is it transitive? Let's look at, this action is transitive. Why is that? Let's look at the orbit of H. What is the orbit of H? This is the set G star H as G is in G. Agree or not? Everybody, by definition, this is the orbit of H, right? It's all G star H as G is in G. Yes or no? This is the orbit. What is the orbit of an element S? It's the set G star S as G is in G. Here my element S, little s, is a subgroup, is a conjugate subgroup of H. Now what's the orbit of H itself? A G star H as G is in G. Agree or not? By definition. Now what is G star H? By definition, what is G star H? Look at this.
The right side.
G, H, G inverse. Very good. Thank you. As G is in G. Now what is this? What is this set? Isn't it the set S?
Yes.
Look at the set S. This is the set S. So this action, how many orbits do I have? One orbit, which is the whole set. Hence, G acts transitively on S. Or S is a transitive G set. S is a transitive G set. Okay? Are we good here? So far so good? It's clear. Great. Now what is the orbit stabilizer here? Well, what is the stabilizer of H? The stabilizer of H, what is that? This is the set G and G, such that G star H is equal to what? Everyone? H. Yeah, very good. What is G star H? G H G inverse is equal to H. Right? What is this? This is just the NGH, right? Look at the definition of NGH. So NGH is a subgroup of G Are we good here? So far so good. Yeah? Are we following? Yeah. It's a bit fast? Okay. Any questions on this? Ask. Yeah. Transitive means you have only one orbit, which is the whole set. Are we good? Is it clear? Okay. So NG is a subgroup of G. And okay, so now if G is finite, let's apply the orbit stabilizer theorem. G stab H is equal to orbit of the size of the orbit of H, right? Agree? So what is the stabilizer of H here?
MG. No, it's
It's the normalizer, right?
yes.
Agree? Just replace. What is the stabilizer of H?
MGH.
NGH, right? So G NGH is equal to the size of S. So how many conjugates do I have of H? It's the index of the... How many elements do you have in an orbit? If this orbit is finite, it's the index of this stabilizer. Okay? Is it clear? Any questions on this? Any questions on this? Okay. Now let's go back to prove Sylow's third theorem. Oh, where is everything? repeat the proof. Okay, so for the final, you're only in charge of the second and the third Sylow's theorem, proving them. Okay, I will give no exercise on them. Okay, you're just in charge of proving them. The key idea, the most important point of the proof, at least for us now, is that the fact if you have a P group acting on a set, then the cardinality of the set is congruent to the number of fixed point mod P. This is the theorem we proved last time, and this is a very important theorem for us. Very important. Okay, so please make sure you know this, and we will use this theorem now. Sylow third, let's restate it again. Let P be a prime number, and G a finite group of order P to the k times m, where k is an n, and GCD Pm is 1. Then the number NP of Sylow P subgroups satisfies NP is congruent to 1 mod P, and NP divides. Let's prove this. Proof. Let P be a Sylow P subgroup of G. And let S be denote the set of conjugates of P. Now, by Sylow's second theorem, which stated that any two Sylow P subgroups are conjugate, S is the set of all Sylow P subgroups. S is the set okay? What is the size of a Sylow P subgroup of G? P to the K, right? The Sylow P subgroup has maximal power of P, size P to the K. We know from the second theorem that any two Sylow P subgroups are conjugate to each other. So this set, that are the set of conjugates of P, is the set of all subgroups of order P to the K. Is that argument clear? I tell you that any two subgroups of size P to the K are conjugate to each other. So if you pick one subgroup of order P to the K and you take all its conjugate, you get all the subgroups of order P to the K. Okay, is that argument clear? Yeah. Now P acts on S. We know that G acts on S, but P also acts on S. How does it act? P cross S to S. You take Y in P, star X P X inverse. It's the same as this action, right? Y is in P and X is in G. Right? It's the same action as G on S, but I restrict it to P. Are we good here? It's the same action of G on S, but I restrict it to P. Now, what did we see last time? We saw that P is a fixed point of this action. Why is that? If y belongs to P, what is yp y inverse? Y star P, which is yp y inverse is equal to what? If y belongs to P, yp y inverse is equal to what?
P.
P, right? Are we good? Multiply P by an element in P on the left, what do you get? P. Multiply P by an element in P on the right, what do you get? P. Right? The claim is that P is the only fixed point. P is the only fixed point of this action. Let's prove this. Suppose that P prime in S is a fixed point of this action. Of the action of P on S. This is a very good argument. This is a very, very nice argument. There are other arguments, but this is the shortest one I've seen. So suppose that P prime is an S is a fixed point of the action. What do I need to show? I need to show that P prime is equal to P. We showed P prime is equal to. Okay. Now P prime is a fixed point. It means that the orbit of P prime is equal to what? P prime is a fixed point. So y star P prime is equal to P prime for all y and P. Agree or not? So far so good? What does this mean? Hence, for all y and P, y P prime y inverse is equal to P prime. Hence, if y is in P, then y belongs to the normalizer of G of P prime. So far so good. What is the normalizer of G in P prime? It's the set of all G in G, such that G P prime G inverse is equal to P prime. So far so good. Hence, P is contained in NGP prime. So far so good. We also have that P prime is contained in NGP prime. This should be clear. If x belongs to P prime, what is xp prime x inverse? P prime. So, if x belongs to P prime, then x belongs to the normalizer of P prime. So far so good. Okay. Now, this is a nice one. So P prime and P, P prime and P are subgroups of NG P prime. Right? P prime is contained in NG P prime, P is contained in NG P prime. So P and P prime are subgroups of NGP prime. Is that good so far? Great. Now, P prime is inside. Both are inside P prime, which is inside G. Yes, sir.
But we know that there's subsets. How do you know that there's subgroups? Because themselves are groups.
Yeah.
Okay.
They're groups. It's a group. It's a group. It's a group. It is a group.
Okay.
Yeah. Very good. Yeah.
So we can prove something is a subgroup just by proving it's a group and proving it's a subset.
Yeah. Exactly. So what's a subgroup? It's a group on its own right.
Yes.
Exactly. Right. Great. Now, do we see this? Do we see how to finish this? What is the? How many powers of P divide G? K.
Just
Yes.
well, it's just an answer.
Oh, okay. Yeah. What did you want to say?
Yeah, it's like you have k powers in G, and then you have k powers in like each. So then we only have room for them to be the same.
Exactly. How? Very good. How many powers of K do you have in P and P prime?
The same one.
How many? Say it. Say out loud. Say it. Yeah, say it. Don't hesitate. Say it.
K.
K. Exactly. Right? Okay? So what is the size of P and P prime? It's P to the K. What is the size of G? It's P to the K times M, where M is co-prime to P. Right? How many powers of P you have in NG? If you have K powers of P here and K powers of P here, inside how many powers of P you must have? K, right? So far so good. Is that clear? Hence, NGP prime has size P to the K times L, where GCD LP is 1. Is this argument clear? Is this number theoretic argument clear? Yes, sir.
Can you just explain or clarify why both P and P prime have cardinality?
Oh, they're Sylow P subgroups.
Oh,
Okay? Did I write that?
yeah, but
Yeah.
just like that.
Yeah, by definition, exactly. Okay. Are we good here so far? Are we good here? Hence, I can say that P and P prime are Sylow P subgroups of NGP prime because they have the maximal prime power dividing the size of NGP prime, right? What is the maximal power of NGP prime? What is the maximal power of P dividing NGP prime? K. What are the size of P prime and P? P to the K. So P and P prime are Sylow P subgroups of NGP prime, by definition. Okay. Now what does the second Sylow theorem says? That they must be conjugate. The second Sylow theorem says that any two Sylow P subgroups must be, read it, must be what?
Conjugate.
Conjugate. Hence, therefore, by Sylow's second theorem, P and P prime must be conjugate in NGP prime. Not only in G, but in the smaller subgroup which is NGP prime. So far so good. What does it mean to be conjugate? Hence, there exists, let's say Z over Z in NGP prime, such that Z P prime Z inverse is equal to P. So far so good? Definition of conjugate. Now if Z belongs to ng P prime, what is Z P prime Z inverse? P prime. This is P prime. Hence P prime. Z belongs to the normalizer of ng P prime. So Z P prime Z inverse is equal to P prime. Okay? Is it clear? Very cool argument.
I'm not sure
Why? What does the normalizer of P prime means? How do you check that an element belongs to the normalizer? If Z P prime Z inverse is equal to what? P prime. This is the definition of the normalizer. Right? So Z P prime Z inverse is equal to what if Z belongs to the normalizer? P prime. So what is the normalizer? Is the set X in G such that X P prime X inverse is equal to P prime, right? If Z belongs to the normalizer, then Z P prime Z inverse is equal to P prime. And hence P prime is equal to P. Now let's finish the proof. I'll raise here. P is a P group. P is a P group. And S is a P set. Whoa, man. I have a P set, okay? Hence, and the action of P on S has only one fixed point. Now, by a class theorem, we know that the size of S is congruent to the number of fixed points. Mod P. How many fixed points do I have? One. And the size of S, it's just the number of Sylow P subgroup. Right? The size of S is just NP. And NP is congruent to 1. Are we good here? Okay, now, is it clear? Just apply the theorem from the previous lecture. If G is a P group and S is a finite G set, then the number of elements in S is congruent to the number of fixed point mod P. Okay? Remember the theorem we have seen? It's a very important theorem. Okay, so you should know it. You should know how to prove it, know how to use it. I don't know what else, know how to prove it, know how to state it, know how to prove it, know how to use it, and repeat. Okay? Great. Now, why does NP divide M? So the first part is done. Why does NP divide M? This should be more obvious. Well, not more obvious, but easier to establish. NP divides M. Why is that? Yes?
By the proposition we proved just before,
Exactly.
we get that size of S, which is the number of P subgroup, but also the number of conjugates.
By the previous proposition, thank you. Very good.
We get size of S is equal to the index of.
Yeah, sorry, I'm turning my back. Sorry, but yeah, go ahead. Yeah, no, go ahead.
Get size of S is equal to the index of the normalizer in G.
Very good.
And then, since we established that the normalizer had the GCD, but we said that it was PKL where
Yeah.
it had the GCD, then you could just.
So the normalizer. Very nice. Very nice. Okay, so but we have to say that L divides M, right? You have P to the L, where L divides M. Very good. Yeah, very nice. Thank you. By the previous proposition, but I will do it in a more general way. Okay? I'll do it in a more general way. By the previous proposition, what did I want to say? By the previous proposition, NP. Very nice, very good. Right? Now, I know that P is a subgroup of NGP. It's a bit stronger. P is a normal subgroup of NGP, but let's not worry about that too much. Okay, P is a subgroup of NGP. And G is a finite group, of course. So, GP right? This is NP, so this is M, because G has size P to the K, times NP okay? So NP divides N. Yes?
And how do we end up having NPG? I don't understand on the right
Oh,
side.
shoot. Thank you.
Oh, okay.
Thank you. Okay? So NP divides M. Okay, so we're done for the Sylow theorems. The goal was just to give you a small overview what is waiting for you in your next algebra courses. We won't apply this. You just have to know the proofs of theorem 2 and 3. Why is that? The key part of I don't want to say the key part, but one important part of theorems 2 and 3 is that the set of fixed points, the cardinality of the set is congruent to the number of fixed points because a P group is active. Okay, this is the key part that you need to know the most. Okay, so yeah. Okay, so this is it for Sylow theorems. Yes, sir.
The theorem statement and the proofs.
Yeah. Yeah. Okay. Great. Now I'll talk a bit about the Coset representation stuff. I think there is a way that I stated it that is more efficient than the other. So I'll state it this way. But I mean, so the whole idea for you was to rederive it every time. I think most of you don't like this. If you just have a theorem that you can apply, then I will just give you the theorem. Okay, we'll just review of Coset representation. So I'll say a theorem that you can use immediately. Okay, let's do that. Usually I expected you to redo everything every time, but now you have the theorem, you can use it. Okay, if you prefer that. You prefer to use a theorem immediately or to rederive it every time? To use it immediately? Okay? Great. Okay, so let H be a finite index subgroup. Here, let's put it